Hey everyone, Prompt here. I hope everyone had a great start to the New Year's and a pleasant end to their last semester. Right before winter break, though, we all had our finals, and I was tutoring maths to a bunch of friends, calculus in particular, and during one of our chit chat moments, one of my friends pointed out that, hey, she's going to biology. Why does she need to even know this? Am I going to find a derivative of my hand speed while I'm dissecting a frog? Oh, please help! The knife won't move unless it finds its instantaneous velocity. Well, we all had a good laugh back then. But looking back, I definitely wish I had responded with something else. There was definitely a use for math and biology. So, hey, why not make a video about all of that? This is How to Build an Organism, Episode 1. Why Biologists Need Calculus. Please like and subscribe. Hit the notification bell. This took my entire winter break to make. Please send help. So, to get the elephant out of the room, things such as recording data of bacterial growth, filling in spreadsheets of data, plotting out that data, and finding out the errors of measurement in the experiment, this kind of math is statistics. Which I think is kind of obvious why it's useful, so I won't be getting into that stuff this time. Now, what I'm interested in is calculus. The stuff many biology students dread and want to avoid doing. What are biologists supposed to use calculus for, one may ask? Integrating a virus with respect to a cell? So, I'm here to hopefully convince you that indeed there is definitely a use for calculus in biology. And here's a gist of it. First, it gives you extra headspace to provide deeper insight into biology and allow us to explore our wildest imaginations. Wow, that sounds like a big claim. So, without further ado, let's dig in. Let's go back to that bacteria from earlier. Let's say that one of the scientists got infected by this pesky bacteria. And in one day, he has 50% or half the chance of spreading the disease to another person. So, what I mean by that is say there are 4 infected and 4 healthy. The infected can either not spread or spread the disease. The chance is half, so on average 4 infected will have 2 of them that actually spreads the disease. Let's say for simplicity that one person only spreads to one other person. So let's play a little guess game. Over time, what is the pattern of spread going to be? Is it going to increase constantly every day? Blow up exponentially? Or sort of taper into some threshold? And let's say there is a really large number of susceptible people, so the limit doesn't really matter. Go ahead, pause and think about it. So, when you have a hard problem in math, it's most useful to break it down. 4 people means they'll infect 2 more people. So let's write this in a more mathy way. And multiply that out by the time passed, just to make things more general and applicable for every day. Speaking of general, let's replace the stick figures with words. And by the end of day 1, we end up with 6 people infected in total. So let's go over that again, just for clarity. So yesterday there were 4 people infected, and by half a chance we have 2 extra people that got infected today. So in total, by the end of the day, we have 6 people infected. And let's move on into the future for day 2. Just to repeat what happens on day 2. 3 more people got infected, and in total we have 9 people infected at the end of the second day. In fact, let's compact this even more. We're going to rewrite everything with variables. yi plus 1 is just the total of people infected at the end of the day, and yi is the total for the previous day. And this is what we call abstraction in math. Now, let's see why this is useful. First of all, we don't have to waste time thinking about stick figures anymore. We can just keep plugging the thing into Excel or some spreadsheet program and let it reiterate just to get the numbers. Heck, we can even plot the thing to find the pattern. We can even easily change how many people we have at the start while we're at it. This is what we call the initial condition. So the initial condition in this case is how many people we start with, say 4 and 10. Now, let's compare this to the stick figure method, which is kind of what we can only think of if we didn't abstract this or use like higher level math. It kind of is annoyingly clunky, isn't it? So here's why abstraction is so useful. It gives you extra headspace so you can do more stuff. And for example, it allows you to see the deeper problems with this model. Pause the video if you want to try and uncover this error on your own. So here's the biggest problem. We assume that the whole thing reiterates only after 1 day has passed. But in reality, John could have been to the gym in the morning, and Brian could have been eating out late at night. If we divided the time into 24 hours, this should fix the problem, right? So this is going to be more realistic since you're adding to the total in hours instead of in days. It's more precise, it's more realistic. But then again, you can divide the time in 1 hour into 60 minutes, 60 minutes into 60 seconds, and so on and so forth until you reach pretty much Planck time. It won't solve the problem. So, let's take a look at our equation. And what we can do is that we can move this to the other side and let delta t, the time that elapsed, say like 1 hour, 1 day, 1 second, be as close as 0 as possible. Not exactly 0 because we'll be dividing by 0 otherwise. And I'm quite sure that those of you who have already taken calculus know what's about to happen. So, when delta t is very close to 0, we can rewrite the whole thing as dt instead. And this is what we call the derivative, but I'm not going to show you how to solve this particular equation here. But if we solve for y, this whole thing ends up yielding this equation here. Hey, this is an exponential function. And by writing it like this, we can actually confirm that it is the exponential growth that we saw earlier. And it's not some other function, say like an x squared, an x cubed. By the way, y0 just means the initial condition, so how many people we started with, same thing. So this is what it looks like when you change the initial condition. You see how the curve is kind of affected by it. So to wrap this little section up, we took a really clunky problem, abstracted it so we can actually plug in various different numbers, in essence, give us extra headspace. And truly understand the change and the pattern that is at play here. And it is these two layers above here that give us the deeper insight into biology that we want. Now, imagine, my friend, when you become a biologist and say you're working in ecology, studying an ecosystem with foxes and rabbits, and you're figuring out ways to conserve this ecosystem. You know, make sure they don't go extinct because they're cute little animals. The good first step will be to consider how the populations of both animals would change over time. Maybe the rabbit population rises to a certain extent, followed by the foxes that have lagged behind a bit. The rabbits get in too much and start plummeting, which is followed by the foxes plummeting. Is it possible with this that somehow the foxes don't have enough food and go extinct, or the rabbits run out of food, or get overly hunted and go extinct as well? And how do you even know that it is this pattern for sure? Well, Let's use our friend abstraction once more to analyze this. Earlier, this was how I set up the equations. But what I didn't take into account earlier was that there is a certain chance that a person can also recover from the disease as well. So the change now doesn't only consist of an increase of infected people, but we also have a second contribution. We also have to subtract the number of people recovered as well. We can use the same thinking for our ecosystem. There are two things that contribute to the rabbit population: the rabbits being born per day and the rabbits being hunted. Likewise, the foxes would also change based on the same thing: foxes being born and foxes dying off of natural causes or starvation. So let's dig deeper. The number of rabbits being born is dependent on how many rabbits there are. So let's say a rabbit has an X% chance of reproducing. That means, say, 4 rabbits would make 4 times X% rabbits. And this is indeed reminiscent of the disease spreading case we saw earlier. And indeed, if you plotted the rabbit population alone without any other factors, say it's not being consumed at all, it would grow exponentially. To simplify a little, let's replace X% with alpha. And that's the first contribution. Let's look at the next one. The fox's death per day should kind of follow the same logic. More foxes present means more foxes dying because the chances are constant, and the chance is delta in this case. Now, here's a trick here a bit. This depends on both the rabbits and foxes. More foxes means more rabbits are hunted, but having more rabbits also means the foxes are also going to have an easier time catching lots as well. It's kind of like a buffet for the foxes. We cap that off with probability beta, and let's move on. Same logic applies to the number of foxes being born per day. More foxes means the more they mate, and more rabbits means the more the food source, therefore energy to reproduce. And let's use a different constant this time, since it may not be the same as the rate of rabbits being eaten. And here we go. Here's the abstracted model that describes how the animal's populations change over time. And here it is in action. You may have noticed that initial conditions determine so much in this case. Not only does it determine the shape of the graph, but it also determines how frequently it moves up and down. See the little white bar on the left there? If you compare it to both graphs, you see that it's not the same. So, we're not done here yet. Instead of plotting the number of foxes against rabbits over time, like we did earlier, we plot the foxes against the number of rabbits instead. This type of plot is what we call the phase plot. It allows you to see the phases of evolution, so to speak. So, by abstracting even further and sacrificing our detail of time, we can gain an even deeper insight into our populations. First of all, upon inspection, you can see that the curves orbit around some sort of point. This is what we call a fixed point. We'll definitely come back and cover what this exactly is down the line, but bear with me for now. One of the biggest takeaways from this graph is that if you take a look at the orbits nearer to the point, you'll find that they don't fluctuate as much. This corresponds to a pretty stable ecosystem. But if we move further away, you see that these populations fluctuate more uncontrollably. The highs of highs and the lows of lows, so to speak. If the animals were to, say, be heavily hunted at the lows, this could lead to extinction. If you're trying to conserve multiple ecosystems, this is really valuable information. You can decide which one needs more care and attention, and which one you just need to occasionally check up on. One other observation that could be useful is that if your initial conditions are on the same curve, they will trace out off the same curve. Imagine you want to get a good catch and you know what curve you're on. You can easily predict when you're going to start packing and hunting instead of staying home and waiting. So, first, we start by fumbling around, not really knowing what to do with anything of the task we're given. And now we're able to gain valuable insights into how these populations change over time, enough to even be able to predict and alter them. In a sense, having the ability to explore them further. Which brings me to my third point. Well, speaking of wild, let's do something that is really crazy as it gets. Let's try building a computer out of living things. This is pretty much the core of the new field of synthetic biology. Quite a new field. It started almost 22 years ago. Back in its early days, though, back in 2000, they definitely started simple. The goal of one of the papers that originated synthetic biology was to construct the easiest form of digital memory on the bacteria E. coli. How it works is that, say, the E. coli begins glowing green. I'm going to call this state 0. We can add a chemical that represents writing it into state 1, which turns it red. And note, even if we remove the signal, it will stay red. It only goes back to 0 in green if it receives a write 0 signal, which is another chemical. Here's how it works on the genetic scale. Add write 1 on the whole, and the whole left wing is disabled, never to return. It's usual if you remove write 1, it still stays red. But as soon as you write 0, the left starts being enabled, and the right is now disabled. If you feel unfamiliar with these components, be sure to check out the previous video in this series. Questions immediately pop up when you're designing these types of genetic circuits. How much of my chemicals do I add? Do I just dump the whole barrel in just to make sure it locks in? How would I design my repressor X and Y? What type of repressor should I use? What if X binds tighter than Y? What if X degrades faster than Y? Questions like these. If we didn't know any better, if we want to answer these questions, we would have to do countless experiments to make sure everything is optimized. That's neither imaginative nor really good for your research budget now, is it? So this is what scientists back then did. They came up with a model that describes the whole genetic circuit, and here it is simulated in the phase plot. So let's analyze this model a bit. Don't worry, we're not going to derive the whole model. It's going to be the content for another episode down the line. But here we go. The constant in red describe the properties of X in RFP. RFP is red fluorescent protein, which is the stuff that makes it glow red. For example, how tight it represses, how fast it degrades, yada yada. And likewise in green. Let's take a look at one specific constant, B. B describes how much the protein degrades. Say you make some Y, and some of it goes to repress the right side, but well, some of it degrades away. This is what we mean by degradation. Bigger B means more degradation. And now you can ask questions like, what's the perfect B? So using the same simulations, you can test this out. Say you want to pick between two proteins. One has smaller B and one has a larger B. Which one would you pick? You see now, by having different B's affects the system a lot, as you can see here. If you plot this little thing out, you can see that the left one has more green color to it, and the right one has a mix of red and green that makes yellow. So you kind of want to pick the left one if you want to go with the discrete 1 and 0 result. But if you aren't really that concerned with, you can go ahead and pick the right one instead. My point is that we haven't done any experiments yet up until this point, yet we've already designed two different color variants. And these simulations barely took any effort to set up. Just took a while to run, but doesn't take weeks like experiments. Let's take a look at a few more examples. This time, instead of changing degradation, let's change how sharply it or cooperatively it binds to DNA. We see at the end that this value is crucial. When you reset the system back to normal after purging it all of the chemicals, we see that the one with the bigger N, the one on the right, is that the one that actually sticks to the same spot. It holds in the memory, it doesn't change back. The one on the left, however, just flows wherever the fixed point goes. That means that it doesn't remember anything. So, of course, pick the right one. And this is what we call bistability. If we take a look at each of the fixed points, see on the right has 2 and the left only has 1. Each of the ones on the right corresponds to an almost definite 1 and 0. And the one on the left doesn't have that sort of separation, so it doesn't really remember anything. Here's if I alter other properties of the repressor. Check it out. Say if I increase the equilibrium constant, or how tightly it binds, or if I change B from 0 until some really big number. And indeed, this process of creating models, altering the properties, and simulating them isn't only used here. It's also been used to design oscillators, pretty much the computer analog of CPU clocks, as you can see here. They did also use differential equations. Design logic circuits, essentially like baby computers, just in living things. And heck, they even did it for making digital displays. So, to wrap it all up, we've used calculus to give us extra headspace by means of abstraction. The extra headspace gives us room to gain deeper insight into biology by simulating reality. And last but not least, it allows us to explore our wildest imaginations, to play around with our variables and find out if it actually works. So, why do biologists need to learn calculus? Well, if I were to go back in time, and here's the answer I'll give. It's literally like an enhancer for your biological mind. We're using it to do better biology. We're not just doing math for just math alone, though doing that is also important. But we're using it to gain so much more from biology than we could ever have wished for. Thank you so much for watching. Please like and subscribe, hit the notification bell. I'll see you next time.